Hey there, welcome back. So previously I've made a video about forces and turning effect, but in this video it's the same chapter, it's the same topic, but I'm going to explain it in a better way. And also I just want to let you guys know that I'm going to use this physics course book to teach this chapter. And if you have this course book, do go to page 58 and 59 and you'll find this chapter. And if you are interested on this book, you can check it out in the link below. So to start with, turning effect, it's the same as moment. Okay? So the formula of turning effect is T E equals to force times perpendicular distance from the pivot. Okay, the most important thing is what I've realized is that most people did not realize the word perpendicular distance, and they tend to calculate the wrong turning effect. So it's very important that perpendicular distance, which means 90 degree, which is right angle, perpendicular distance from the pivot. Okay? So let me just erase this because I need more space. So I will just put force is F times D. Okay? So realize that if you want to increase the turning effect, it's either for us to increase the force or increase the distance, the perpendicular distance from the pivot. Okay, so let's try an example. Let's try an example here. This is a wood or a metal bar. So the pivot, I will put a pivot here. Okay, so pivot means the point of rotation, the point where the rotation occurs, we call it as pivot. Pivot, it's equals to point of rotation. Okay, the point where the rotation occurs. So let me just redraw this thing, rotation. Okay, so let me just draw it nicer. Okay, so the pivot here, and let's say we put an object here, and the mass of the object may be 1 kg. So if we convert it to force, F equals to ma, which is F equals 1, the gravitational acceleration, which is 10 ms, so we will put it as 10 newtons. Okay, so 10 newtons. 10 newtons. Okay, so the force of this guy, it's 10 newtons. Okay, so the distance is the perpendicular distance from the pivot, which is here, the perpendicular distance here. So the distance of this, it's maybe 5 cm. Okay, 5 cm. So as soon as if I put an object here, it will have a turning effect. So we can put it into the formula. And before we calculate the turning effect, I just want to quickly say that we have clockwise movement and anti-clockwise movement. Okay, so if you do not know what's a clockwise and anti-clockwise movement, it's basically if you have a clock or a watch like this, so our clock will go to this direction, right? So we will call it as clockwise moment, okay, clockwise. And for anti-clockwise moment means you want to prevent the clockwise moment, which means you have to go the opposite direction, which we call it as anti-clockwise moment, okay. But for clock is clockwise and anti-clockwise, yeah, like this. So I'm just going to erase this. Erase this real quick and erase this as well. So in this case here, we will have clockwise movement or clockwise turning effect. So TE turning effect equals to force. The force is 10 times perpendicular distance from the pivot, which is 5 cm. Let me just write this as unit. 10 newtons, 5 cm. And the answer is 50 N cm. Okay? So this is how the formula works. I'm just going to quickly erase this first. And the another thing that is, just now I had said that clockwise and anti-clockwise moment, right? So for this clockwise moment and anti-clockwise moment, if the turning effect is equal, so there will be no turning effect or reach its equilibrium. Okay, so I'm just going to put this maybe right here, and I'm going to arrange this to here. I'm going to put a star, so it's easier for us to see. And if you want to take a screenshot, or you want to copy in your notebook, or you want to copy on your iPad, just go ahead and copy it. Feel free to copy it on your notebook or iPad because it's very important in physics. So what do I mean is, let's use black pen, right? Black pen, and again a metal bar, okay, and the pivot here, the pivot is in the center, so I will just put it as 5 cm, and here 5 cm as well. Okay, so it's in the center. So right now, if we apply a force, maybe let's say we apply 10, okay, 10 newtons here, 10 newtons. Okay, so before we do the calculation, this diagram right here shows us that it's in equilibrium, which means no turning effect. So turning effect, and I can prove it because turning effect equals to turning effect. Hold on, I just want to quickly erase this. Okay, just let me put it up here a little bit. Okay, so we know that clockwise and anti-clockwise moments, they will reach its equilibrium, which causes no turning effect. And here it's clockwise moment. I will just write clockwise here, or clockwise moment. And right here it's anti-clockwise moment. Oops, anti-clockwise moment. Okay, so anti-clockwise moment equals to clockwise moment. There is no turning effect. And right now we can put it in the formula. We know this is anti-clockwise moment, which is F times D equals to F times D. If you put it in this 5 cm, which is perpendicular distance, the perpendicular distance, 90 degrees, right angle. Okay, so it will be 5 here, then I will put here 10 newtons, and the F here, the force will be 10 newtons as well, times 5. Okay, so 50 equals to 50, which if I cut it, there will be no turning effect. So you can see here, because 50 equals to 50, if I move it here, 50 minus 50 equals to 0. And it's true, no turning effect. So there is no turning effect. So which means it has reached its equilibrium. Okay, no turning effect. So let us try another example, a more complicated one, but it's the same, the principle is still the same, the formula still works the same way. Okay, as long as you understand the basics of turning effect and forces and those and the moment, you will be alright with that. Okay, just keep in mind the distance will be perpendicular distance. Okay, perpendicular distance. So right now let me show you let me draw one diagram here, and here it's the pivot. So right now let's say we apply a force here, we apply a force at the end of this metal bar. If we apply a force, let me just use the red pen. We apply 10 newtons here. Okay, so the distance, this is a tricky one, the perpendicular distance, right? So let's make it easier to see. Okay, the perpendicular distance, if there is a line here, so the perpendicular distance here, it's perpendicular distance from the force. But some people, or like me last time, I do the calculation in a wrong way. It's because I thought the distance is here to here. Let me just use a blue pen. I thought the distance would be here to here, but it's wrong. It's perpendicular distance. Right here, it is not 90 degrees, so the distance is not here. We take the distance, this one, this line right here, horizontal line. Okay, so let us just calculate the turning effect. So F times D, the force which is 10 times, let us just say here, let's put 20 meters and 20 meters, so 200 and m. Okay, so that is how it works. Okay, so I just want to talk about the formula again. Let me just erase this real quick. So the formula is moment equals to force times perpendicular distance, distance. Okay, so as long as the turning effect occurs anywhere, like just now and the second diagram that I had drawn just now, okay, as long as the turning effect occurs, which means the moment is going to happen here. Okay, so for this diagram right here, if the turning effect occurs, the turning effect will appear here. Okay, so not to get confused. So that's it for this video. I hope you have understood what I have explained just now. And again, if you have this physics course book, because most GCSE students, they use this course book. If you have this course book, do go to page 58 and 59 and you will find this chapter, forces and turning effects. And that's it. I will see you in the next one. Bye.